Hello student, I am Dr. S.L. Munde, Assistant Professor Department of Mathematics, Sri RLT College of Science, Akola. Dear student, in this lecture we will start Meromorphic function theorem. Before going to start Meromorphic function theorem, we will see definition of the meromorphic function. So what is the meromorphic function? So let us suppose that G be a region. The function f is analytic on a region G except with the isolated singularity as a pole in G are called as meromorphic function. Okay, the function f is analytic on G except with the isolated singularity as a pole in G, that is called as a meromorphic function. For example, f of z equal to z square upon z minus 4 mod z less than 6 is a meromorphic function with pole z equal to 4. Here z equal to 4 is the pole in the region mod z less than 6. So mod z, which represent a circle whose center is 0 and radius is 6. Okay. So here z minus 4 is a meromorphic function with the pole z equal to 4 in this region mod z less than 6. Okay. So now we will see the argument principle on a meromorphic function. The argument principle is stated as let f be a meromorphic function in region G with zeros at z1, z2, zn. So these are the zeros of the function and poles at p1, p2, pm according to their multiplicity. If gamma is a closed curve in G not passing through zj and pk for j equal to 1 to n and k equal to 1 to m. Then we have to show that 1 upon 2 pi I integral over gamma f dash z upon f of z dz, this is dz equal to summation j equal to 1 to n index of closed curve gamma at point zj minus summation k equal to 1 to n eta of gamma pk. Okay, so this is the statement of the argument principle. Now we will see the proof of this principle. So here we have given f of z is a meromorphic function in a region G with zeros z1, z2, z3. Okay, with the poles p1, p2, pm. Okay, so here we can say that f of z has a zeros at z1, z2, zn. For the multiplicity of the proof, we assume that zeros are with multiplicity and poles are simple poles. Okay, that is the of order 1. So therefore by using the definition of the multiplicity, analytic function with multiplicity, there exists a analytic function f of z on G and which is defined as f of z equal to in numerator z minus z1, z minus z2, z minus zn divided by z minus p1, z minus p2, z minus pm. So these are the zeros, these are the poles into g of z. Here g of z is not equal to 0 for zj and pk, where j equal to 1 to n and k equal to 1 to m. Okay. Now we will take the log on both sides. So taking log on both sides, so we will get log f of z. So here we will apply the formula log a by b, that is log a minus b. So that is log z minus z1 plus log z minus z2 plus log z minus zn in first bracket. Second bracket, that is minus log z minus p1 minus log z minus p2 and so on log z minus pn. Okay, n2 means this, that is plus log g of z by using the logarithmic property. Now we will take the differentiation with respect to z. Now we will differentiate this equation with respect to z. Okay, so derivative of log f of z is 1 upon f of z into derivative of f of z, that is f dash of z. Okay, So similarly, we will take the derivative of the right hand side, that is 1 upon log z minus z1, that is 1 upon z minus z1. Derivative of this term, that is 1 upon z minus z2, and so on. Derivative of this term, that is 1 upon z minus zn. Minus derivative of this term, that is 1 upon z minus p1. Derivative of this term, that is 1 upon z minus p2. 1 upon z minus pm, plus derivative of this term, that is 1 upon g of z, into derivative of this, that is g dash of z, we can write. Okay, now we will multiply on both sides 1 upon 2 pi r, then we will integrate with respect to along the curve gamma. Okay, so multiply 1 upon 2 pi r on left hand as well as right hand side, and take the integration over the curve gamma. Okay, so we will get these steps. Okay, so multiplying 1 upon 2 pi r and taking integral over gamma on both sides. Okay, so we will get these steps. Okay, now here we will use the definition of index of closed curve uh, to each integral z minus z1, z minus z2, z minus zn, z minus p1, z minus, and so on. Okay, so by using the definition of the index of closed curve, we can write as index of closed curve at curve gamma at a point z1. Okay, so it is written as eta of gamma z1, and this can be written as eta of comma z2, and this can be written as, and so on, eta of zn. Similarly, by using index of closed curve, this can be written as minus eta of point p1 minus eta of p2, and so on, minus eta of pm, plus 1 upon 2 pi r. So this term as it is, integral over curve gamma g dash of z upon g of z, g of z into dz as it is. Okay, so this term can be written as in the summation term. Okay, so this is also can be written as summation j equal to 1 to n eta of z, eta of gamma zj, where j equal to 1 to n, minus summation k equal to 1 to m eta of gamma phi k. Okay, and this term is as it is 1 upon 2 pi integral over gamma g dash of z upon g of z dz as it is. Okay, now from this equation, if you observe that here g of z, which is a analytic on region g. Okay, so therefore we can say that the g dash of z is also analytic on region g. The ratio of both, the ratio of g dash of z upon g of z is also analytic. Okay, so therefore by using the Cauchy's theorem, the value of this integral will give the 0. This will integral can be written as integral over cos gamma g dash of z, g of z dz equal to 0. So multiplying 1 upon 2 pi, that is, you will get this term is 0. Okay, so hence we can write left hand side, that is 1 upon 2 pi integral over cos gamma f dash of z upon f of z dz. So this is the left hand side, equal to summation eta of gamma zj, j equal to 1 to n, minus eta of gamma pk, k equal to 1 to m. Okay, so this is the complete proof of the argument principle. Okay, now we will see the another argument principle, generalization of the argument principle. We can see there the generalization of the argument principle. What is the statement of the generalization of the argument principle is, let F be a meromorphic in the region G with zeros at Z1, Z2, Zn and poles P1, P2, Pm counted according to their multiplicity, and let G be an analytic function in G and gamma be a closed curve in G which is not passing through Zj and Pk, where J equal to 1 to n and K equal to 1 to n. Then we have to prove that 1 upon 2 pi integral over cos gamma g of z into f dash of z upon f of z dz equal to summation j equal to 1 to n g of zj eta of gamma zj minus summation k equal to 1 to m g of pk eta of gamma pk. Okay, so this is the statement of the generalization of the argument principle. Okay, now we will see the proof of this theorem. Okay, so here we have given f is a meromorphic function in the region G with the zeros z1, z2, zn and with poles p1, p2, pm. Okay, So here f is a given analytic function with zeros z1, z2, zn and poles p1, p2, pm. Okay. Now for the simplicity of the proof, let us we assume that the zeros of the multiplicity of order. Okay, so by using the definition of multiplicity of zeros and order of the pole, so there exists a function that is h of z in region G, and which is defined as f of z equal to z minus z1, z minus z2, z minus zn divided by z minus p1, z minus p2, z minus pm into h of z. So here h of z is not equal to 0 for zj and pk. J equal to 1 to n and k equal to 1 to m. Okay, so now we will take the log on both sides. Okay, so log a by b into h of z, that is log a by b plus log h of z. Then we will use formula log a by b formula, that is log a minus log b. Okay, so by using the formula of log, we can write down this term, that is log f of z equal to log z minus z1 log z minus z2 plus and so on log z minus zn minus log z minus p1 minus log z minus p2 and so on minus log z minus pm plus this term, that is log h of z. Okay, now we will take the differentiation with respect to z. Now, okay, so take the differentiation with respect to z to this term. So we get derivative of log f of z, that is 1 upon f of z into derivative of f of z, that is f dash of z. Okay, derivative of this term, that is log z minus z1, that is 1 upon z minus z1 plus 1 upon z minus z2 and so on 1 upon z minus zn minus derivative of this term, that is 1 minus 1 upon z minus p1 and 1 upon z minus p2, this is z. Okay, and so on last term will be 1 upon z minus pm and derivative of this term, that is 1 upon h of z into derivative of this, that is h dash of z we can write. Okay, now we will multiply on both sides 1 upon 2 pi I into g of z. Okay, and then we will integrate along the curve with respect to z along the curve gamma. Okay, so multiplying on both sides 1 upon 2 pi I into g of z, and then we integrate with respect to z along the curve gamma. So we get 1 upon 2 pi integral over curve gamma g of z. This is the multiplied term f dash of z upon f of z dz equal to 1 upon 2 pi integral over curve gamma g of z upon z minus z1 dz plus and so on 1 upon 2 pi integral or curve gamma g of z upon z minus zn dz minus term 1 upon 2 pi integral or curve gamma g of z z minus p1 and last term will be this and plus 1 upon 2 pi 1 upon 2 pi integral or curve gamma g of z h dash of z upon h of z dz. Okay, now here we will use the definition index of a closed curve. Okay, so by using the definition of a index of a closed curve, this can be written as g of z1 eta of gamma z1 g of zn eta of gamma z2 zn. Okay, zn minus g of p1 eta of gamma p1 and so on gamma of pn eta of gamma pn and last term will be as it is 1 upon 2 pi integral or gamma g of z h dash of z upon h of z dz as it is. Okay, now here if you see that, so this term can be written as plus term, then we will write minus term. Okay, so this term plus term can be written as summation j equal to 1 to n g of zj eta of gamma zj in summation form minus second term, that is minus term minus summation k equal to 1 to n g of pk eta of gamma pk and last term plus 1 upon 2 pi integral or curve gamma g of z h dash of z upon h of z dz as it is. Okay, now if you observe here, okay, if you observe here g of z, which is a given analytic function. Okay, so here g is a analytic on a region G. Okay, so therefore we can say that h of z is also analytic and hence h dash of z is also analytic. Then the ratio of this term will be a analytic function. then the whole term will be the analytic functions. Okay, so therefore by using Cauchy's theorem, the value of this integral will be 0. Okay, so that is integral over core gamma g of z h dash of z h of z is equal to 0. So putting the value 0 in this term, we will get this step. Okay, so left hand side is 1 upon 2 pi integral over core gamma g of z f dash of z upon f of z dz equal to right hand side, that is summation j equal to 1 to n g zj e of gamma zj minus summation k equal to 1 to m g of pk e of gamma pk. Okay, so this is the complete proof of the generalization of the argument principle. In this way, in this lecture, we have seen argument principle, argument function, definition, argument principle, as well as the generalization of the argument principle. So in next lecture, we will see some problems on argument principle.